Hey everybody, this is Merm. We are ready to do part 2 of physical behavior of matter. Today is focused on gases. So let's get rolling here. Name and draw some gases you're already familiar with. Okay, we definitely know about oxygen and carbon dioxide. Those are gases that obviously you're breathing in oxygen and using it for respiration, and you're breathing out the carbon dioxide from the sugars that you break down. Methane is another gas, CH4. All of those are nonpolar molecules, and all of them have very weak, basically no attraction to one another. So when we think about our particle diagram, we want our molecules to be very spread out. Oops, lost my molecules. All right, so make them be really spread out far away from each other. If you wanted to specifically do oxygen, you could make each one of these be diatomic, and then I really have a perfect particle diagram. Oops, they gotta be touching. There we go. All right. Okay, visualizing gases. So it's really important in chemistry, you know how we're always acting things out, to really picture what's going on, because it will help you understand it and really think about it and think about the molecules. So describe the location of gas particles in relation to each other. So gas particles definitely spread out. They do not like being close. They like to be spread out as far as possible. So imagine our Ranger gym as a closed container full of gas molecules. Students. Each student is a gas molecule found in a random position throughout the gym. Everyone is walking in a straight line. Since everyone started in a random position, no one is walking in exactly the same no one's walking in exactly the same line, and sometimes they bump into each other or into the wall. When they bump into each other, there's no attraction or repulsion, just a new direction they start walking in. Does everyone walk at the same pace? Nope. Neither do gases. Different gases tend to move at different speeds. When temperatures increase, what happens to the movement of particles? All right, so think about this. If the temperature is increasing, that means your kinetic energy is going up. So the particles are going to move faster. If you are a gas in the gym and the temperature has just increased, what would happen to the total number of collisions? They would definitely increase. So think about it. You're walking in a straight line. All these other people in the gym are walking in straight lines. If you start moving faster, chances are you're going to have more collisions. When temperature decreases, what happens to the movement of the particles? So they are going to slow down as it gets cold, less kinetic energy. If you are a gas in the gym and the temperatures just decrease, what would happen to the number of collisions? So it would decrease. What would happen to the number of collisions if half the gym was closed off and all the gases had to stay in the only open half? All right, in the open half only. All right, so now we only have half the volume. So if you just cut the amount of space that I can walk down or walk around in, I am definitely going to have more collisions because, okay, so I'm picturing the whole gym. I used to have all this room to walk and walk and walk and walk and walk, boing, 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 boing. But now you just cut my space in half. So now I can only walk in this area. So I am definitely going to increase the amount of collisions I could have if you decrease the volume. Okay, so here I have particle diagrams of a solid, a liquid, and a gas. So my solid, the particles are just vibrating. And here they are able to flow past one another. And here they're able to freely move. So that's the first thing I noticed between the solid, the liquid, and the gas. These have very strong intermolecular forces of attraction, and these definitely have the weakest intermolecular forces of attraction. These have a fixed volume and they're definitely occupying the space of their container. These ones are going to take the shape and the volume of the container, meaning they're really going to spread out and take up whatever room you put them in. If you think about, oh, I forgot to write shape here. Okay, so a solid has a very fixed shape and it has a very fixed volume. If you think about a liquid also has a fixed volume. Like if you have 50 milliliters of water, it's 50 milliliters no matter what container you put it in, but the shape takes the shape of the container. All right, and then there's one more thing that I want to add here. This gas is compressible. Sorry, I got to write it over here. Compressible means that I can change the volume of this. This is my only one that I can actually change the volume of it. So because it takes the shape and the volume of the container, we can say it's compressible, which means I could actually push on it and make it fit into a smaller space. You can't do that with a solid or a liquid. Place a star by all the properties of a gas. So go ahead and do that. Okay. This video shows these little molecules moving around. So let's see if I can play it for you. There they go. So as these bouncing balls are moving around, we got to think about what do they have in common with and how do they differ from gas molecules. So something that I'm noticing right away that's a similarity is they are moving in straight line. But a difference that I'm noticing is that when they collide, they slow down and they almost fall to the bottom. Yeah, see how some of them are just rolling along the bottom here? That's definitely something gas molecules don't do. What I want you to think of, instead of just bouncing balls, remember those screensavers where it would have a little ball and it would go boing, 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 boing. I know you love the sound effects. That is really how a gas molecule moves. Constant straight line motion. When they hit each other, it's like an elastic collision. It doesn't fall and lose any energy. It just keeps on going. All right, factors that affect gases. So we already talked about a couple of them. Temperature is definitely one of them. So over here we could have like, what if you increase the temperature and what if you decrease the temperature? So when you increase the temperature on a gas, so I think it's really helpful to think of something like a balloon. So imagine if I had a balloon. I'm going to inhale and I'm going to exhale and I'm going to blow up this balloon full of gas. And then I'm going to just think about the air inside of this balloon. And I tied off the balloon, so it has a very specific volume right now. If I heated it up, so I brought it into, maybe I went down to like the pool area. You know, when you go down to the pool area, it's always like so much hotter than every place else, or sometimes my classroom this year, warmer than other places. The particles would actually expand. And so as they expand, that means I'm going to increase the volume. My balloon is going to actually get larger. Because those molecules are colliding and spreading out and moving faster. They're colliding, they're spreading out. Okay, but if instead I brought my balloon outside and it's really, really cold outside, the gas molecules are now going to condense. And so when they condense, they are going to be closer together. So the volume is going to decrease. There's going to be less collisions and it's going to occupy less space. Everything is going to be closer. All right, so temperature is definitely something that affects gases. Another thing that affects gases is volume. So I was just speaking of volume. Each of these sort of have an impact on each other. Volume is the amount of space that you have available. So if I increase the volume, that allows my molecules to spread out. That means I'm going to have less collisions. So again, I could think of the balloon again, but this time I want to have the exact same amount of gas. I just want to have a bigger space. So I got to think about my balloon getting larger and larger and larger. So that means the molecules are able to spread out more and more and more. But it got larger without me putting more air molecules into it. So either from heating it, something like that, it just allowed it to take up more space. I could also think of my air balloon, and now if my volume is smaller. So again, I don't want to change the number of gas particles, but now they're in a smaller space. So now they are much closer together. And so if I have that same number of particles in a smaller volume, they are going to have more collisions. Because again, these have now changed to what I have here for each one. So I really have to remember I'm thinking of each factor on its own, and I'm thinking about the effect that it will have on my overall gas particles without changing the number of gas particles. And then the last one I want to think about is pressure. All right, so if I exert pressure on my balloon, so I've blown up this balloon, there's a specific number of gas particles in it, and I now push on it. So imagine me pushing on the balloon. I'm increasing pressure, and when I increase pressure, I decrease the volume. It's like going, like you're crushing it. So when I decrease the volume, I am going to have more collisions, and I am making those molecules be in a very tight space with each other. If I think about decreasing pressure, oh, that's like creating a vacuum. It's like creating a space where there's no pressure, there's nothing on it. Now everything can really spread out. And so if it's spread out, then it's going to increase the volume and there's going to be way less collisions. It's actually weird to think about decreasing pressure, like not having any pressure on something. It's a weird concept. All right, we'll keep moving forward. Okay, so for all of these, I have a visual to help walk you through it. So based on the data shown in the experiment setup given, describe what happens to the volume of a gas if you increase the temperature. So we have been talking about these factors, and now I'm actually showing it to you. So here's my first temperature, and you see the size of the flame. And here's my second temperature. Oh, and you see this, and you see this. So now it is much hotter. So when I increase the temperature, I increase the volume. So this was my first volume, and it is very small compared to my second volume. So the particles have now spread out because I'm increasing that temperature. All right, this relationship is what we call directly proportional. So the graph, as you increase the volume, you increase the temperature. So you can think about like a low volume has a low temperature, and a high volume has a high temperature. So there it is. That is a directly proportional graph. Pretty easy to think about the temperature volume one. All right, now pressure. So when you think of pressure, I want you to think of each of these collisions as pressure. Collisions to equal pressure. And the collisions can be with each other, and the collisions can be with the wall. So if the volume doesn't change, and you increase the temperature from 200 to 400, what has happened to the pressure? So my temperature is 200. Here's my temperature is 400. It went from 1 to 2, so it doubled. So double the temperature, double the pressure. We know as temperature increases, molecules move faster. This means the molecules will collide with each other and the walls, like whatever container it's in, more when you increase the temperature. This is also directly proportional. So if I think about low pressure, low temperature, and high pressure, high, this is my directly proportional graph again. As one goes up, the other goes up. That's what it means to be directly proportional. Okay, using the diagram, explain the effect of increasing pressure on volume. Okay, pulling up increases the volume and decreases the pressure. Okay, this one is having the opposite effect. So if I increase the volume, I decrease the pressure. More space here leads to not as many arrows, and those arrows were my pressure. But here, if I decrease the volume, I increase the pressure. So I really need to think about, oh, okay, so these were my increase the volume, I decrease the pressure, or I can also write here that when I decrease the volume, I increase the pressure. Those are my relationships. And I know usually I write those out as words, but I'm doing increasing and decreasing as arrows. Okay, so now I want us to think about how this graph would look. All right, when I have a really low volume, so over here I had a really low volume, I had a lot of pressure. So my point on the graph has to be up here, high pressure. And when over here I had a high volume, then I want to have a low pressure. So this graph ends up looking like this. This is called inversely proportional. And so pressure and volume have an inversely proportional relationship. As one goes up, the other doesn't go up. It's not directly proportional. It's inversely proportional. As one goes up, the other goes down. Oops, just skipped a page. Okay, so air inside a basketball. Unfortunately, this video is no longer available, but I knew that that was going to pop up and tell me that it wasn't available. So instead, I still want you to think about a basketball. And I want you to think about, a second ago, it showed that little air pump next to it. So here's my basketball, and here's that pump. And you know how there's that little needle, and you put the needle in to pump up a basketball. And you have to go here and you have to push this down. And when you do, you are adding more air particles. So you are increasing the number of gas particles that are inside of this. And it causes it to increase the volume, and it definitely increases the pressure, because they are going to collide with each other and they're going to collide with the wall more and more and more. And if you kept doing it, I mean, there's always a chance that that basketball is even going to explode if the pressure is greater than the material of the basketball can withhold. So I just want you to think about pumping that air inside of a basketball, because it gives you a really good visual of what pressure means. So each of these little gas molecules inside of here can collide with each other, and they can collide with the wall. The more collisions they have, the more pressure there is. So again, collisions for us is a relative way of measuring pressure. There are actual ways of measuring pressure, but visually, it's very helpful to think of each collision that's going on as pressure. Okay, so what's fabulous for us in terms of doing calculations is that all these relationships that we've been talking about, everything that we will have to calculate is all in one formula. So this is all on table T, and this is called our combined gas law. P is the pressure, V is the volume, T is the temperature. Easy to remember, plus it's on table T, you don't have to remember it. 1 is all of our initial, and 2 is all of our final conditions. So if I know at the beginning what the pressure, what the volume, what the temperature is, I can calculate changes. So if I know, like, hey, I changed this and this, what do you think the final volume will be? I can calculate it. This is a mathematical formula, so we're going to start punching in these numbers and solving. When we do these, there's a whole bunch of rules that we've got to make sure we follow. The first one is so important. Anytime you put temperature into the ideal gas law formula, it has to be in Kelvin. So if I'm given Celsius, I just remember, oh, I have to add 273, and that will give me K. So make sure you're in Kelvin for all gas law formula problems. If you need to know STP, STP is standard temperature and pressure. It's all on table A, and again, use the temperature and K. Identify all values in the question and label them. So that is a habit that I do, and I'll show you right from the first problem that I do with you. When you label them as V1, V2, P1, P2, T1, T2, it really helps you put them in the right place in the formula and solve. All right, cross multiply to solve for X. So we're just doing some algebra here. If necessary, round your answers to the 10th place. We can try to use sig figs. Sometimes it works out for us to use sig figs and sometimes it doesn't. Always check your units and always show your work. All right, so let's get rolling here. I'm going to do a bunch of them with you, and then you will have the remainder of time to work on practicing. So a balloon has a volume of 4.2 liters. All right, that's my first volume. Oh, and it's at STP. So that means my standard temperature and pressure, that's my T1 and my P1. All right, so my T1 and my P1. When heated to 400 K, okay, so that's going to be my new temperature. So I'm putting T2 there. And the pressure is lowered to 0.5 atmospheres. So that's my P2. What is the new volume? So what I'm going to solve for is V2. That's what I'm looking for. So the first thing I've got to do is grab my reference tables, and I'm going to go to table A, and I need to find my P1 and my T1. So I want my pressure to be in atmospheres because this is in atmospheres. So standard pressure is 1 atm. And then standard temperature is 273 K. All right, I am now at the point that I'm ready to plug everything into my formula. My formula is P1 V1 over T1 equals P2 V2 over T2. And so now I'm ready to plug everything in. So I have one, oops, sorry. I have 1.0 times 4.2 divided by 273 is equal to 0.5 V2 and 400K. Okay, so when I'm solving for V2, this is my X. This is what I want to stay all by itself on that side. That is my X. So to cross multiply, you go down here and you go up here. So now I am physically punching into my calculator. I am punching 1 times 4.2 times 400 equals. And then I go divided by 273 equals divided by 0.5 equals. So that means my V2 is equal to 12.3. I'm going to go with the 10th place instead of the sig figs because it looks like I'd only use one sig fig and that wouldn't make any sense at all. So I'm going to keep it at 12.3. The unit here was liters, so I'm going to keep liters. So it makes the most sense for me to use the 10th place here in this calculation. All right, so if you lost me on the math, when you were typing into the calculator, you can go 1.0 times 4.2 times 400, because I have all three of those numbers up top, and then go divided by 273 equals divided by 0.5 equals, and you will have your answer because you have divided your answer by both 273 and by 0.5. If you prefer to do it another way that you like to do in your calculator, that is fine. You're really just doing algebra. All right, a gas has a volume of 67 liters at STP. When heated to 700 K and the pressure remains the same, what's the new volume? Okay, so this is my first volume. They want me to find the volume, so I got to find V2. They're heating it. Oh, this is my T1 and this is my P1. They're heating it to 700, so this is my new T2. The pressure remains the same. Okay, so P1 V1 over T1 equals P2 V2 over T2. Okay, if something stays the same, I can literally cross it off on both sides because I would be cross multiplying by the exact same number, which means it would cancel each other out. So I do not have to include it, and that's why this formula is so fantastic. You can use it when you have all of the factors, and you can use it when you have just two of the factors. Okay, so I'm going to plug in my values. 67 at, okay, I need standard temperature, and I remember that that's 273 K, so 273 is equal to V2 over 700. Okay, I want to solve for V2, so that means that needs to stay right there. This is going to cross multiply, so I take my calculator, and I go 67 times 700 equals divided by 273 equals, and my V2 is equal to 171.8. If I go to the 10th place, I mean, I could have easily just rounded this to 172 liters. If we're not doing sig figs, it really doesn't matter which you rounded this to. Okay, and I know it probably sounds crazy that I'm not using sig figs, but a lot of these calculations are a multiple choice question, and they haven't given me a lot of sig figs in the actual question, so it's hard for me to give sig figs in my answer. All right, next one. A gas has a volume of 390 milliliters at 300 C. Oh, okay. Right away, I got to add 273 because this is not in Kelvin. So that gives me 573 K. Okay, this is my T1, this is my P1, and this is my V1. All right, at standard temperature and pressure, what's the new volume? So again, I'm finding V2, but I got to change the temperature to 273 K. That is my T2. And so my P2 is going to be, and I go look on table A again at standard temperature and pressure. And so if I want to use atmospheres, standard pressure is 1.0 atm. Okay, so I'm going to fill in my values. So my first pressure is 1.4. My first volume is 390 milliliters, and my first temperature is 573. My second pressure is 1.0. I'm trying to find the volume. That's what I'm going to solve for. And 273 is my new temperature. Okay, oops. I keep hitting something that's making it do that. Sorry. All right, so I'm going to cross multiply, which means you're going to get multiplied up there, you're going to get multiplied up there, and V2 stays right there. So I solve for V2. So I punch into my calculator, 1.4 times 390 times 273 equals, and then I go divided by, so 573 times 1 is just 573, so I'm dividing it up by 573, and I get 260. So V2 is going to equal 260, and then I look up here, that was in milliliters, so my answer is in milliliters. All right, let's do another one together. A gas has a volume of 390 milliliters. Okay, so that's my first volume. At 400 K, so that's my first temperature. At 50 milliliters, ooh, I have V2. So now I have to find what's the new temperature. So there are no P's in this, so I don't have to use it in my formula. So this time I'm setting up 3 90 over 400 is equal to 50 over T2. Now, T2 is what I have to solve for, and it is on the bottom. That is not okay. So what I'm going to do is I am going to cross multiply to have it be up here, and I'm going to do the 390 down there. So I'm going to cross them with each other. And the 400, I'm going to cross up. So I got to make this look all neat again. I cross the T2 up. So T2 is going to equal 400 times 50 over 390. So that was me cross multiplying. And now I'm going to punch it in my calculator. 400 times 50 equals, divided by 390 equals. And I get T2 is equal to 51.3. If I go to the 10th place, and this is in K. So I look at it and I go, okay, does this make sense? It was 390 milliliters at 400 K, and now it's all the way down to 50 milliliters. So it shrunk incredibly. And so to shrink incredibly, it must have been very cold. 51.3 K, very, very cold. All right, let's keep moving on. A gas with a pressure of 4 atmospheres. So you can also pause me if you want to solve the problem yourself and then see if you got the same answer as me, because I'm doing the exact same steps every single time, and pretty soon I'm setting you off on your own anyways. So you can pause me. All right, so gas with a pressure of this atmosphere. Okay, so that's my first pressure, and that's my first volume, and that's my first temperature. At 400 milliliters, so that's my new volume, and oh geez, this is my new temperature. What is the new pressure? Okay, so this time I'm solving for P2. Okay, so I've got 4.0 times 111 over 200 is equal to P2, 400, and 300. Okay, I want my P2 to stay right there. So I'm going to cross this one up and I'm going to cross this one down. And so I'm going to punch this into my calculator. 4 times 111 times 300 equals. And then I'm going to go divided by 200 equals. And then I'm going to go divided by 400 equals. And I get P2 is equal to 1.7. And so now this is ATM because this was ATM. And there's my answer. All right. And next slide is time for you to start working on your own. So take your time. Use the rules. The rules are right back on the page earlier. Ask for help if you're getting confused. Check my answer key. I also have videos on my YouTube. All right, so go ahead, work on your own, help each other. And remember, you're just using one formula and plugging each thing into it. All right, miss you all. Bye.